Okay. All right, guys. Welcome back to week four's live interaction session. This is me, Rajnandan, here again. I'll be taking your session as usual. And yeah, and I welcome you all once again to this week. Without any further delays, let's quickly, but before that, a couple of announcements. So the first thing is the session on next week, which is basically the session on 24th August. Okay, that is preponed to Tuesday from 6 p.m. to 8 p.m. That is the session on 24th August is preponed to 20th August, Tuesday from 6 p.m. to 8 p.m. Just one second, I'll just do the clarifications here first. Yeah, so the session on 24th August, Saturday, from 3 p.m. to 5 p.m. is preponed to August 20, that is Tuesday, from 6 p.m. to 8 p.m. And one more session, which is the session on 31st August, uh, that is Saturday, which was supposed to be from 3 p.m. to 5 p.m., is postponed to September 8th, Sunday, from 3 p.m. to 5 p.m. So these are the couple of announcements. So this readjustment, please be very clear that this readjustment is just for these two sessions only. That is for the sessions on 24th and 31st August. The 24th August session is preponed to 20th August, Tuesday from 6 p.m. to 8 p.m. The usual session on 31st August is postponed to September 8th, Sunday from 3 p.m. to 5 p.m. Please be clear that this readjustment is basically for just these two sessions only, and all other remaining sessions we will have it on the usual Saturday time slot from 3 p.m. to 5 p.m. For everyone, I will also post it in the coming days in the discussion forum also, such that it comes in record for everyone. And for the ones who missed this class, you can have a look it in a discussion forum and get to know about the rescheduling of just these two sessions. I once again repeat, this rescheduling is just for these two sessions only. That is for the session on 24 August and 31st August. 24 August is preponed to August 20, Tuesday from 6 p.m. to 8 p.m. And the session on 31st August, Saturday, is postponed to September 8th, Sunday, 3 p.m. to 5 p.m. All other sessions apart from this will be conducted on the usual Saturdays from 3 p.m. to 5 p.m. as we all are meeting right now. Okay, I hope this is clear. You will separately get emails regarding this. You don't need to worry about that. You will separately get emails regarding this rescheduling very shortly. So yeah, so you don't need to worry about remembering this and that. So you will get to know about that individually. So you'll get emails as well as it will be posted in the website. And also I will try to post it in the discussion forum of the group as well, such that it also comes into the record. Okay. And yeah, also you will get emails, as I said, separately, uh, sharing this information. Okay. All right. So the second thing, I thank you all for using the discussion forum, and I think some of you have really appreciated the quality of questions that we are solving in the live session. So I really thank you all for taking your time out and watching these live sessions. Maybe attending the sessions live, or maybe watching it on YouTube, and so on and so forth. So I really thank you and for taking a time to basically seeing how the session goes and then appreciating the quality of questions is very much a good, it's a great gesture from everyone, and I really thank you. I, on behalf of all the team members of this course, really thank you for your appreciation. Secondly, I received the query regarding one of the sessions. I think regarding one of the questions in one of the sessions on week 2. So I am on it. So I just now saw the query. So I am on it. I will post the clarification about the query on the same email thread itself. So you can have a look, or you can revert back to the discussion forum and have a look. I will post that maybe by today or latest by tomorrow. About the query, I'll address the query. I'll just need to have a look at the question once again, and then I'll post it in the same email thread where the query was raised. Again, thank you very much for using the discussion forum. I really I should have answered it early, but I really missed the question that was raised there, so I just answered it today. Uh, but yeah, thank you very much for actively participating in the discussion forum. Okay. So these are a couple of announcements and couple of things that I felt should be said. All right. So now, without any delay, we will quickly start off with today's session, and you guys know by now the drill. So the drill is we will basically have a recapitulation of what we learned in week 3, and then we will proceed with a very interesting topic once again in heat generation, in heat transfer, which is known as heat generation. We will look into some good cases and special cases of heat generation in maybe slabs and cylinders in today's class. But before that, let's quickly have a recap of what we did in the previous week. So in the previous week, we looked into something which is known as the conduction resistance network. This, I would say, is another way of basically calculating the heat transfer in basically calculating the rate of heat transfer in conduction, where we looked into the fact that, for instance, in a slab, if there was no heat generation and the mode of heat transfer is conduction, of course, and there is no heat generation, and if my direction of heat transfer is one directional, then we said that an alternative way of calculating the rate of heat transfer is by using something which is known as the conduction rate network analysis. And I said that this network philosophy that we saw here, it also, it also can be extended to radiation and convection as well. Okay. But nevertheless, the idea is that you need to you need to understand that when you write the rate of heat transfer, for instance, if we look into this special example, we saw that this phase was maintained at temperature T1, this phase was maintained at temperature T2, and so long as there was no heat generation, which now means that if my thermal conductivity is also constant, I can represent the temperature profile as a linear profile. And in that case, I can use the resistance network, which renders the fact that I can write the rate of heat transfer as the difference between the temperature between these two phases divided by all the resistances that come into the picture when I take two temperature nodes. For instance, in this case, there is only one resistance that is basically being offered by this slab. Okay, and that's why it becomes L by K. Now, we also discussed on what assumptions that this resistance network is valid. And thereafter, what we did is we solved couple of problems, couple of good problems, I would say, related to this resistance network. Okay, and then just one second. Yeah, so we saw a very good problem that was related to resistance network. For instance, this problem one, where there was a film and a substrate, and in order to heat and in order to bind the film and the substrate, we provided a heat flux. The idea was to calculate the magnitude of the heat flux provided that the temperature at different nodes were known. And we assume, considering the assumptions that we discussed, we basically first drew the resistance network and then calculated the unknown heat flux that was required to maintain the temperature between the film and the substrate at a temperature T naught. Okay, so this is something that we discussed in the last class, and this was an important problem. And in the second problem, we looked into how do we write resistances in cylindrical geometries, and uh, how does basically the resistance formula look like for a cylindrical geometry. And we saw that for cylinders, this can be written as ln of r naught by ri divided by 2 pi kl, as you can see from here. And then we also looked at something which is known as critical radius of insulation, because remember we said that it's just that not it's just not that if you go on adding insulating material, your rate of heat transfer will always decrease. So up to a certain thickness of insulation, which we saw, and which of course you have derived its expression for cylindrical geometry in your theory classes, I mean in your lecture classes, and you have seen that if we go on adding insulation up to that critical radius of insulation, your rate of heat transfer obviously will decrease, and thereafter it increases. And after a certain thickness beyond the critical radius of insulation, we saw that the rate of heat transfer was even more than it was when there was no insulation. Okay, and yeah, you also need to remember that this critical thickness of insulation is not applicable for, I mean, this critical thickness of insulation is not applicable for your, like, Cartesian geometries, for instance, like slabs, but it is applicable for cylindrical geometries or spherical geometries. Okay. Next, what we did is we basically solve another like very practical problem which was related to the air conditioning load of aeroplane windows. And we saw that instead of using just a single glass pane, we looked into this picture that how typically airplane windows are designed. And we saw that instead of using a single glass pane, we took some realistic values of temperatures, as you can see here. And we saw that instead of using a single glass pane, if we use a glass pane and a sandwiching layer of air, the rate of heat transfer essentially decreases. Okay, and we basically figured out, and using, of course, using the resistance analogy again, we basically figure out what would be the heat flux for the two scenarios. The first scenario, as you know, is basically using a single glass pane in between the two temperature limits. And in the second scenario, we use two glass panes sandwiched by an air layer in between. The very reason so as to why basically the rate of heat transfer decreases when you use an airspace in between is basically because of the fact that thermal conductivity of air is much less than the thermal conductivity of glass. As you can see, thermal conductivity of air is 0.024 and thermal conductivity of glass is around 1.4. So it's around 2 order of magnitude less than glass, and this is typically the reason why air acts as a very good like resistance. Airspace acts as a very good resistance to the heat transfer. And this resistance, as I said, is desirable. This resistance, as I said, is desirable typically because we always want to minimize the cooling load of the aircraft, because that typically leads to uh, the more and more use of fuel, which the aircraft is eventually carrying. Okay, but this is something that we saw in the last class, and I'll stop here for some time. If you have any doubts, you can ask me, or else we will proceed with the important topic for today's discussion is heat generation in slabs and cylinders. Okay, so I'll stop here for some time, maybe a couple of minutes. If you have any doubts, you can ask me, or you can like type it in your chat box, or else we will proceed with we what we will do for proceed with the agenda for today's discussion, which is basically heat generation in slabs and cylinders. So this topic is once again related to the topic that you are going to submit the assignment for the week 4, that is again heat generation in slabs and cylinder. So again, this is important in context of it's important as a whole, as I said, and it's also important in the context of like solving problems related to your assignments as well. Again, the agenda is that I will not exactly verbatim solve the problem that is there in the assignment. This is not the principle of this live interaction sessions, I believe. But the idea is that the problem that you solve here in these interaction sessions, this will very much assist you in solving the problems that you will eventually see in your assignments. And I hope by now you have realized that in this course. Okay. All right, so we'll wait maybe for 1 or 2 minutes, and then we will begin with the first problem on heat generation that that you will see here in your screen. I hope you have seen it. You can quickly also have a look at the problem. I will anyway explain it, and then we will see how the solution looks like for this case. In the meantime, I'll just check if the recording is going on or not. Yeah, it's going on. All right, guys. If you don't have any doubts, then we will look into the first problem that we are going to discuss today. So let's see what this problem says. It says that consider a one-dimensional plane wall with constant properties and uniform internal heat generation Q dot. So there is this plane wall which has an uniform heat generation of the magnitude Q dot, as you can see. The left face is insulated and the right face is held at a uniform temperature. So what they're saying is that this face is insulated, and the physical meaning of insulation is that there won't be heat flux that will basically escape from this interface to this side, basically because it's insulated. It's the adiabatic condition which we said, which means that whatever the heat that is basically being generated inside the slab needs to be dissipated through this face. Okay. And they have also said that the right face, which is this face, is maintained at a uniform temperature Tc. Now, if this is the scenario, they're asking us, using the appropriate form of the heat equation, derive an expression for the x dependence of the steady state heat flux Q double prime of x. So this is what they have asked us to do. I'll wait here for some time. You guys can read the questions once again, and then I'll show you how the solution basically looks like. All right, so I hope you guys have gone through this question. So let's first begin this problem by stating down the assumptions that we have. Okay, so let's first write down the assumptions. Okay, the first assumption is that, although we don't do this in all the problems, but it's a good practice to start off your problem by writing down the assumptions, and then it gives a clear picture of it gives a clear picture for you also, and also it, like, whosoever is checking your copies, they have a good impression of the fact that you essentially understand the problem, and you are basically you basically know when, so as to when the governing equations that we write uh, are essentially valid, and that basically comes from the assumptions. Okay, so it's always a good practice to write down the assumptions. So the first assumptions, as we have seen multiple times, is that we will consider the steady state condition. Okay, and I would add one line: steady state condition with constant properties, meaning that I don't have anything that is now a function of time. Also, my properties, for instance, in this case, the thermal conductivity is constant and it is not a function of time, or it's not a function of space in this scenario. Okay. The second, the second assumption is related to something which is known as the heat generation. So it says that this slab experiences a uniform internal heat generation Q dot. This means that your Q dot is not varying with space or time. Okay. Of course, it is not varying with time because we are considering it as a steady state condition, but your Q dot is also not a function of space, which means that I have uniform volumetric heat generation. Okay. And of course, the third assumption is also something that we have used and always use multiple times, is that we are considering one dimensional heat transfer. So I would write here heat transfer is one dimensional. Okay. So I hope you guys are clear with the assumptions. All right, guys. So what we'll now do is we will start off with the governing equations. So the next step, as you all know, is basically writing out. So what do we need to do? See, the question asks us to find an expression for the x dependence of the heat flux. So the heat flux come into the picture. So what basically relates the heat flux to the temperature is the Fourier's law, right? So we'll start off by writing the governing equation, which is basically the one-dimensional heat equation, and from there we will try to see how is the flux that will be related to this heat generation that we see. Okay, so the governing equation, the governing equation basically looks something like this. So the heat diffusion equation takes the form in case of all these assumptions that we have seen, considering the fact that your thermal conductivity is constant, it's a 1D heat transfer problem and your heat generation is uniform. And in this scenario, your governing equation, which governs the, it's basically an energy balance only, and which we also know by the heat diffusion equation, looks something like this. So it is d2t by dx2, and this is equal to q dot by k, and this becomes equals to 0. And then what I can now do is, see, I don't want the temperature distribution. What I want is, I want the heat flux. Okay, so what I will now do is, very carefully I will write this as, the first term as ddx of dt dx plus q dot by k equals to 0. Okay, all right. So what I will now do is, I will take this q dot by k to the other side, which means it is ddx of dt dx equals to minus q dot by k. And since we need the flux, and for flux, we can use the Fourier's law, which says that your flux is directly related to the temperature gradient, meaning that we need to evaluate this dt by dx. Now that is rather simple, right? Because we can integrate this equation. Okay, and when we integrate it, of course, we'll do an indirect integration. And then if we integrate it, we'll integrate this with respect to dx. Okay, and then this becomes dt dx, and this becomes minus q dot kx plus a constant c1. All right. So now you guys need to tell me, how do we can evaluate this constant c1, because this c1 is an unknown to our problem, right? So this is very simple, right? That is typically because in your problem it has been stated that for this slab, okay, it has the face on the left hand side is insulated, which means when I say it's insulated, it means that, so what does it mean? So the left face, it says that the left face is insulated, which means that your flux, okay, your flux evaluated at x equals to, so if I take my coordinate system, which is basically here only, so if I take my coordinate system from here, this means that my flux at x equal to 0 is basically equal to 0, and this is the physical meaning of insulation. Okay, which means that q double prime evaluated at x equal to 0 is 0. And now I know that what is q double prime. So q double prime from the Fourier's law can be written as minus k dt by dx evaluated at x equal to 0 is basically equal to 0, which means, so this simplifies to dt by dx at x equal to 0 is 0. Okay, so this is obtained from one of the boundary conditions that we saw. So this is your equation 1, I would say, and say this is your equation 1a, which is basically applying the insulation boundary condition on the left face. So if I substitute 1a, in 1, if I just substitute this value in 1, then what do I get? So I have seen that at x equal to 0, okay, so if I use this in this equation, so at x equal to 0, I have seen dt by dx is basically equals to 0. Okay, that is basically from here, which means that c1 indirectly comes out to be equals to 0. Okay, that is basically using the boundary condition 1a into the equation 1. So the idea is, I will substitute 1a onto 1, okay, And then what I get is, what do I get? So I get 0 equal to 0 plus C1, which means your C1 is basically equals to 0. Okay, therefore, what do you get? Therefore, your temperature gradient dt by dx simplifies to minus q dot by k x. All right, so we are almost done. Okay, we are almost done. So now what do we require? They're asking us not the temperature gradient, but the flux. So therefore, your flux, that is your heat flux, by the Fourier's law is basically minus k times dt dx. And then if you substitute the value of dt dx, which is basically this, into this dt dx, and then what you get is, you get your flux to be equal to minus q dot x. Okay, which means your heat flux is basically equal to minus q dot x, which is basically your answer. Okay, so that's what the question is asking, right? They're asking us to calculate the x dependency of the heat flux. Indeed, the heat flux varies with x, that we all know. And this is obvious, right? Because we know that when we solve the heat diffusion equation, considering the fact that your properties are uniform, it's a 1D heat transfer, and there is a uniform internal heat generation, we know that your temperature profile is parabolic. Okay, that means your T is basically a function of x square. Okay, so if your T is a function of x square, this means that your flux, which is basically the first grade, so it's basically the derivative of temperature with respect to x, will obviously be of order 1. Then that's why your heat flux varies linearly with x. Okay, that's the answer to this question. And again, I would stop here for some time. If you have any doubt, you can ask me, or else we will begin with the next question. I'll stop here again for some time. If you like come into, or if you just have any doubt. And also, like, if you have any doubts, like after this session, you can always post it in the discussion forum. And I think a couple of you guys have done it. I really thank you for that. And then we will address those doubts in the discussion forum, as and when we we gets into the schedule of this course. Okay. All right, guys. So I hope you guys have learned this question well. So let's now begin with the second problem. This is a little bit more involved problem on heat generation, as you can see. So let's try to understand what this problem says. I don't know, there is again some lag that is being happening in my screen, but I hope you guys are seeing it. So I hope this is okay. So I hope you guys can see my second question on the screen. This is there. Anyways, I think it'll be there in your screen. Okay. So yeah, so let's try to understand the second problem. So it says that a plane wall of thickness twice L equal to 40 mm and thermal conductivity K equal to 5 watt per meter Kelvin experiences uniform volumetric heat generation at a rate Q dot, while convection heat transfer occurs at both its surfaces at x equal to minus L and plus L. So again, it's a similar problem, but now with respect to the earlier problem where we saw that it's one of the faces are insulated, now this slab or a wall is now being cooled by a fluid which basically bears a temperature T infinity equal to 20 degrees Celsius. Okay, and it is being convectively cooled by that fluid. All right. So it says that further it says that under steady state condition, the temperature distribution in the wall is of the form T of x equal to A plus Bx plus Cx square, where they have delineated the temperature distribution, where these constants A, B, and C are also given to us. This means that in this case, we completely know what is the temperature distribution that is given to us. Okay. Now, the origin of the x coordinate system is at the mid plane of the wall. That's okay. So the first task that they have asked us, given this physical scenario, okay, given this physical scenario, the first task that they have asked us is to sketch the temperature distribution and identify significant physical features. The second task is to calculate the volumetric heat generation in the wall. That's okay. And the third task is basically to determine the surface fluxes at the right face, which is at x equal to plus L, and at the left face, which is at x equal to minus L. And how are these fluxes related to the heat generation? So it's kind of 4 questions that they want us to solve. I would again stop here for some time. I want you guys to read the question once again and try to frame a physical picture of this question and the underlying like problems that they have asked us to solve for, and then we will systematically proceed with the solution to this problem. Okay. Okay, all right guys, so let's get started with the solution. So first come first, let's first draw the physical picture of this problem. Okay, and then we will see what needs to be done in the like sub questions. So it says that there is a slab. Okay, fine, we have drawn a slab, and the coordinate system of the slab is such that the axis is at the mid plane of the slab, which means that my axis system is something like this. So it's, let's say it's at the mid plane, so maybe something like this. Okay, so this is at x equals to 0, this point is x equal to L, and this point is x equal to minus L. I hope the physical system is clear. Now this slab says that it bears an uniform heat generation of Q dot. Okay, and also the temperature distribution of this slab sorry, so the temperature distribution of this slab is given to be T of x is equal to A plus Bx plus Cx squared. I hope you can see what I'm writing on the screen. I'm sorry there is some lag that is in the screen, and this is related to the network issue here, but I hope you can get and at least understand the problem that we are basically solving here. Okay, so the temperature distribution is given, and the slab is now convectively cooled, okay, by a flowing fluid at its sides. So there is a fluid that is basically flowing. Okay, there is a fluid that is basically being flowed on two of its sides. Okay, maybe in some directions you can pick any of your direction, whichever direction you want. Maybe it can flow in this direction, or maybe your other way around. And they have said that the temperature of the fluid, temperature of the surrounding fluid, of course, is T infinity, which is basically equal to 20 degrees Celsius on both the sides, that is on the right and as well as on the left, which means T infinity is 20 degrees Celsius. Now, one important bit of information is something that they have not given us. They have not said what is the heat transfer coefficient of the fluid that is flowing to the right and the fluid that is flowing to the left. They have also not said that are they both the same fluid, and even if they aren't the same fluid, what basically is the heat transfer coefficient. We may need to find this heat transfer coefficient as a part of the solution. Okay, which means what I'm saying is that the heat transfer coefficient at this right face and the heat transfer coefficient at this left face is not known to us. Okay. So what I will do is I will consider the heat transfer coefficient to the right as HR and the heat transfer coefficient to the left as HL. It may be that HR and HL can be of equal magnitude. We don't know, but a priori we will not assume that HR is basically equal to HL. Okay. All right. So first come first, what they are asking us to now do is sketch the temperature distribution. So for that, we need to see the temperature profile, and we know that the temperature profile is given to us. For instance, the temperature profile T as a function of X, okay, is given as, so what it is given as, so let's see, it is A plus Bx plus Cx squared. So it is A plus Bx plus Cx squared, where this A is given to be equal to what? So your A is given to be equal to 82 degrees Celsius. Your B is given to be equal to minus 210 degrees Celsius per meter. And your C is given to be equal to minus 2 into 10 to the power 4 degrees Celsius per meter square. Okay. So this is what they have given to us. All right. So now let's do the first task, that is basically to plot this temperature distribution inside the slab. So what I would want you guys to do is, what is basically T at x equals to L. Remember that your L. So I think I have not stated the distance. So remember that this distance, basically from here to here, right? Say from here to here is basically twice L. So this distance is basically twice L, and twice L is basically equal to 40 mm, which means that this L is, so this L is equal to 20 mm each on both the sides. That's just the simple math. Okay. Now you guys need to tell me what is basically T at x equal to L. So it's simple, right? It is just basically, you just need to substitute the value of L in the expression of T, which is basically A plus B L plus C L squared. But remember, you need to substitute the value of L as 2 into 10 to the power minus 3. You need to substitute it in meters, typically because your values of A, B, and C's are in meter. Okay, and that's why you need to substitute in meter. And if you just do this math, that's an easy math, of course, just you need to multiply these values. So if you just do this math, you will see that your temperature at x equal to L comes out to be, so I have already done it, it comes out to be around 69.8 degrees Celsius. Okay, that is one thing. Similarly, if I want to see what is the temperature at x equal to, if I want to see what is the temperature at x equal to minus L, just do the same exercise, and you will see that your temperature at x equal to minus L comes out to be, if you just do the math, it will come out to be 78.2 degree Celsius. Okay, so now this means that we have evaluated what is basically the temperature at x equal to 0, okay, and the temperature at x equal to L. So let's now just plot it here. So at x equal to L, it is around 68.9. Let's say this point is 68.9. Okay, sorry, 69.8. Sorry, 69.8 degrees Celsius. And at x equal to minus L, it is 78.2, which means this should be around somewhere here, 78.2 degrees Celsius. So if I now sketch the temperature profile, okay, of course I know it's parabolic. That is basically been evident from the profile that is already given. So this means my temperature profile would look something like this. Okay, it will basically look something like this, which is basically a parabola. Okay, maybe this does not look like a parabola. Maybe I can draw this, and then maybe I can draw this. Maybe I can draw like this, and maybe like this. Yeah, I think this is better. Okay, so now we will see something very important, which I think you guys also need to appreciate. See, even if there is a uniform heat generation, okay, inside this slab, and this slab is being convectively cooled by a fluid which has the same ambient temperature, which is T infinity equal to minus 20 degrees Celsius, then also the temperature profile is not symmetric about the midplane. And this is something that we need to understand why basically this is happening. And this is solely related to the heat transfer coefficient. Okay, if you guys remember, we solved the problem in maybe the last to last class where we saw that if there is uniform heat generation inside the slab and if they are cooled by a fluid which bears the same ambient temperature and the heat transfer coefficient, then the temperature profile would come out to be linear. Okay, but here it did not come out to be linear, meaning that even though the heat generation is uniform and the ambient fluid bears the same temperature, but the heat transfer coefficients on the right and the heat transfer coefficient on the left may not be the same. And that is basically the reason why the temperature profile is not symmetric about your x equal to 0 axis. Okay, and this is what we got when we plotted the temperature profile, which means that you will not see a maxima at x equal to 0. Okay, this will also mean that the heat fluxes, if you we will see shortly that the heat fluxes when we will evaluate here and the flux that we will evaluate here will not be numerically equal in magnitude. In fact, you can sense that the flux so you can sense that the flux on these spaces will of course be numerically be of different magnitude with this flux, and you can also give an idea of what the order of magnitude of the flux would be that we will basically see. Okay, so this is something, these are the something key physical insights that you need to understand from these from the temperature distribution that we draw based on the physical picture that was given to us in this problem. Okay, so I'll stop here maybe for some time. I need you guys to understand and try to observe what we basically saw, and then we'll proceed with the next part of the problem. We have completed the first part, which says that we need to sketch the temperature distribution, and we have already done the temperature distribution, and we have also identified significant physical features. Maybe the first physical feature is that even though the heat generation is uniform and the ambient fluid is at the same temperature, then also your flux, then also your temperature profile is not symmetric about the midplane. The typical reason for this is basically due to the fact that your heat transfer coefficient for the fluid to the right and for the fluid to the left may be different, and that's why your fluxes, because see, this flux that will come out from this surface is directly proportional to the heat transfer coefficient. Okay, and if the heat transfer coefficients are different, for instance, if this heat transfer coefficient is low, then this flux would obviously be low, will be low. Okay, and so on and so forth. All right, so I hope you have understood this. So let's get down to business now. Let's calculate the second part of the problem. So what it says is that what is the volumetric rate of heat generation Q dot in the wall? So they're asking us, if you know the temperature profile, now you need to give me what is the value of Q dot. Okay, so that again we have done it multiple times. So what we will do is we will, as you guys know, we will use something which is known as the heat diffusion equation. So I'll write it now here that using the heat diffusion equation. Okay, so what is the heat diffusion equation? It says that ddx of k dTdx, okay, plus, or maybe you can just write it like this. Okay, I'll show you. So it says that ddx of k dTdx plus q dot equal to 0. Considering the fact, again, see, I have not written the assumptions here, but it's always a good practice when you write it in your home or you write it in your exam, or maybe you are write it in your colleges exam. Always start off with the assumptions, draw the physical picture that we draw here, and then proceed with the governing equations. Okay, that's always a good way of solving the numericals. Okay, so so basically, this is the heat diffusion equation. So what I can now do is, since my thermal conductivity is constant, I can take it out of the differentiation and I can write it as d2t by dx2 plus q dot by k equals to 0. Okay, and then they're asking me to calculate q dot, which means I just need to evaluate this d2t by dx2. This is rather simple, right? Because I know t as a function of x is what? So t as a function of x is a plus bx plus cx squared. Okay, which means my dt dx is b plus 2cx, and my second derivative with respect to x is basically equal to 2c, which means d2t by dx2 is basically equal to 2c. That means I can write this as 2c plus q dot by k is equal to 0. Okay, and from here I can simply write q dot. I can simply write q dot as minus 2ck, and if you substitute the values of c and k, I think they have given us the values of c and k. So your c is minus 2 into 10 to the power 4 degrees Celsius per meter squared, and your thermal conductivity k, I think it is given, or is it not given? It should be given. Yeah, it's 5 watt per meter Kelvin. Okay, so if you do this, this becomes q dot, which is basically your volumetric heat generation, as minus 2 times your c is minus 2 into 10 to the power 4, so this becomes plus, and this becomes 2 into 10 to the power 4 into 5. So if you simplify this, if you just simplify this, your q dot, that is your volumetric heat generation, comes out to be 2 into 10 to the power 5 watt per meter cube. Okay, so this is your first this is your second answer that the question was asking us. So what they're asking us is, they're asking us to calculate the magnitude of the volumetric heat generation. So the magnitude is this 2 into 10 to the power 5 watt per meter cube. Okay, I hope this is clear to you. All right, let's now go into the third part, which is basically part C. So let's try to understand what part C says. Okay, so part C, what they're asking us is, determine the surface heat fluxes Qx at minus L and Qx at L, and how are these fluxes is related to the heat generation. Okay, the second part we'll do it later on. First, let's do this basically to calculate what are the fluxes at x equal to L and at x equal to minus L. And as I have said, these fluxes are not going to be equal in magnitude, and we will see shortly. So the flux basically, so how do we calculate the flux? So I know that from Fourier's law, Fourier's law, my flux, that is q double prime of x, okay, in the x direction as a function of x, is minus k times dt dx, where I have seen that my temperature profile is of the form a plus bx plus cx squared. So you just need to substitute the values. So therefore, if you plug in the value of d2 dx, your flux becomes q of x as a function of x. This becomes minus k, and your dt dx is this. This is, we have calculated, your dt dx is b plus 2cx. Okay, so this becomes what? This becomes b plus 2cx. You already know the magnitude of k, b, and c. So therefore, your flux at x equal to, let's say, minus L is basically minus k plus b minus 2cl. Okay, and if you just plug in the values, but you will see that you will get this value to be around minus 2950 watt per meter square. This is your flux q double prime on x at x equal to minus L. Okay, at x equal to minus L. Maybe I should write it in this way. We're going to write it at x equal to minus L. So this is your one part of the third part. Okay. Similarly, if you do the same exercise, you can similarly find out that your flux at x equal to plus L is basically nothing but minus b plus 2cl. Okay, and if you do this, you will get a value of around 5050 watt per meter square. Okay, so this is your flux qx, where at x equal to L. All right, I hope so far you have understood what we have done. Okay, okay, so what we did is, as we have seen, the fluxes at the surface at x equal to minus L and at the surface x equal to L are not similar, and in fact, forget about similar, if they are not equal to their magnitude. Okay. More importantly, if you see, if we see the fluxes at x equal to minus L, we see a negative sign. See, this negative sign has a very important physical significance. Okay. When I look on this surface, you need to understand what is the direction of heat transfer. So the direction of heat transfer will always take place from a phase which has a higher temperature to a phase which is a lower temperature. Basically, it will take place from the temperature node, let's say 7.8, 78.2 degrees Celsius to 20 degrees Celsius, which means that my flux would be in this direction, in this direction. Okay. Or you can, in other words, you can say that if this slab is generating heat, it has to dissipate heat, and the only way it can dissipate heat is by fluxes from these surfaces and these surfaces. Now, we know that from these surfaces, the direction of flux has to be in the negative x-axis, typically because this phase is at a higher temperature than the ambient fluid. Okay, and that's why when I evaluated mathematically the value of the flux at x equal to minus L, I automatically got a negative sign in its expression, which is basically minus 2950. Now, if I can, if I can similarly draw the similar analogy that in the positive x-axis, looking into the phase at x equal to L, my my direction of heat transfer would be from this phase to the fluid, and that's why the direction of heat flux, which of course is a vector quantity, is in the positive x-axis, and that's why we have witnessed a positive sign in its calculation and in its answer. Okay, so this is something that you guys need to understand. All right. So finally, they're asking one more important problem. Okay, which is basically the fact that they're asking that how are these fluxes related to the heat generation rate. And for that, we will do something that we have done maybe in the first class. So what we will do is we will choose a control volume now encompassing this wall or the slab. Okay, so what we will do is we will choose a control volume. Okay, maybe like this, maybe like this, and maybe like this. Okay, so we'll choose a control volume encompassing the slab, and what we will do is we will apply the law of conservation of energy in this control volume. So what we will do is we will apply law of conservation of energy in the CB meaning my control volume. Okay, so if I apply the law of conservation of energy, which says basically, so I now need to apply, and it should be written in terms of the rate of heat transfer, okay, or the heat flux. You can write it in terms of the heat flux as well. That's completely up to you. So if I write that, what I will get is basically Q dot. So if I do that, what I will get is the energy that is coming inside the control volume. Let's say it is Q dot in, because by energy I only mean that the heat energy, and all other energies we are not considering throughout in this course. Okay, until and unless we have mentioned it otherwise. Okay, so Q dot in, that is basically the rate of heat transfer coming inside the control volume, minus Q dot out, plus Q dot gen, basically the heat that is being generated inside the control volume, and this should be equal to 0. Now, you need to understand that throughout this slab, the temperature is always at a higher temperature to that of this ambient fluid, which means that my slab will always dissipate heat to its ambient and not the other way around. Which means that in terms of the control volume approach, my Q dot in will always has to be equal to 0. This Q dot in will always have to be equal to 0, typically because the slab is always at a higher temperature than the ambient fluid. It is the slab that is being losing heat to the fluid and not the other way around. So that's why whatever the heat that is being generated will be dissipated out and not inside the slab. Okay. So this then simplifies to, so if my Q dot in is 0, this then simplifies to the fact that Q dot gen is basically equal to Q dot out. Okay. So this is something that we got from the energy balance when written in the control volume that we saw. Now here is the catch. So what is Q dot out? Q dot out is nothing but, see, since this heat transfer is basically an 1D heat transfer, this means whatever the heat that is being generated inside this because of this heat generation, it has to be the only way it can go out of this control volume is through fluxes at x equal to L and through fluxes at x equal to minus L. Which means if I write Q dot out, then Q dot out has to be numerically exactly equal to the summation of the flux at x equal to L and summation of the flux at x equal to minus L. And that's why I will write this as Q dot out. Okay, Q dot out is basically equal to the magnitude of, let's say, Q double prime. Okay, I'll say it's, let's say it's the magnitude of Q double prime at x equal to L. Okay, by magnitude I mean that I'm considering the net energy that is leaving the control volume through these fluxes, and that's why I'm considering its magnitude. Okay, and since this is Q dot, these fluxes need to be multiplied, okay, with the area, and that's why this becomes equals to A. Okay, and then it becomes plus Q double prime, the flux evaluated at x equal to minus L. Of course, I'll consider the magnitude times the area. Okay, so what I have, so at x equal to L, I have this flux at 5050. So it is 5050 times the area plus, since I'm considering the magnitude at x equal to minus L, it becomes 2950 times the area. You guys need to understand why I have considered the magnitude. This is typically because I am looking inside the control volume approach and I am seeing what is the net energy that is basically leaving inside the control volume, leaving from the control volume. That's why I have considered the magnitude. Okay, so if you do this, what you will get is you will get it to be exactly around 8000 times the area. Okay, now let's do one thing. Let's try to evaluate this Q gen, because we have already evaluated Q dot, right? We have evaluated the magnitude of this 2 into 10 to the power 5. Sorry, this Q dot, which is basically 2 into 10 to the power 5. So if I now evaluate Q gen, okay, if I now evaluate Q gen dot, it will basically be Q dot, which is the heat generation per unit volume multiplied by the volume of the slab. So what is the volume of the slab? Okay, so multiplied by the volume of the slab. Okay, so what is the volume of the slab? That is rather simple. That is the length of the slab. The length of the slab is basically twice L that we have seen just now. So here, so this entire length is twice L multiplied by the cross section area, which is basically A that we have just now considered. So it is this length L multiplied by this cross sectional area A that will give me the volume of this entire slab. Okay, so this becomes what? So this becomes Q dot, the volume, which is twice L multiplied by A. And if you evaluate, it's very interesting. If you evaluate this Q dot, so Q dot is what? So Q dot is 2 into 10 to the power 5. 2 into 10 to the power 5 multiplied by 2, and your L is 20 mm, which basically becomes, okay, so it's 20 mm, which basically can be written as 20 into 10 to the power minus 3 times the area. So if you do this math, what you will get is you will exactly get it to be 8000 times the area, which means your Q dot gen is basically equal to 8000 times the area. Okay, and this means, see, this is exactly equal to your Q dot out. Okay, and this is what we are actually proving from the energy balance, right? See, the energy balance says that your Q generated has to be equal to the Q flux that is being that is going out from the surface. And numerically also, we have seen that your Q dot out, which came out to be equal to the summation of all the fluxes through the areas, which came out to be around 8000 times the area, and your Q dot gen also came out to be 8000 times the area, which means that the steady state energy balance indeed holds good in this case. Okay, and that this is how the third part of the question, that this is how your flux is basically related to the heat generation inside the slab. Okay, so this is the last part of the question that we are required to solve. Okay, I would again stop here for a couple of time. I'll give you a homework here. The homework is based on this. Okay, so I'll write here that try. So what you need to do is try at home. What you need to do is at home, you need to evaluate. So evaluate the two heat transfer coefficients, HR, that is basically the heat transfer coefficient on the right face, and HL, which is basically the heat transfer coefficient on the left face, based on this information that we have seen. Okay, so this is something that you require to do at your home, and of course we'll discuss this in the next class. If you cannot, I'll show you how it can be done, but at least give it a try at your place. Okay, so with this, we end the second question. I would stop here again for a couple of time. You can you can think about this, how we proceeded it, how did we came up to the conclusion that the energy balance indeed holds good if we also follow a control volume approach. Why and how did we conclude that the heat transfer coefficient on the right and the left face, even though we have the same fluids, are different, and so long and so forth. So I believe this is a very good question, and it will give you it will give you a plethora of insights into heat generation that is being taking place. Yes, the problem was a little bit simpler, but it gives you a magnitude of insights into the temperature profiles that can take place inside heat generations, taking places in slab, and so long and so forth. Okay, so I'll stop here for a couple of time. I'll I'll just come in 2 minutes. I'll fill my mug, and uh, I would ask you to reflect on the solution of this question. Try to like understand how we did and why we did it. And after this, we will look into something which is known as heat generation in cylinders, and we will solve a similar problem. However, in cylindrical coordinate systems, where we will see how basically we need to do with heat generations inside a cylindrical body. Okay, but uh, but before that, like I would stop here for some time. I would ask you guys to like reflect on how this question is being done, and I would just come here. I'll just come in 2 minutes, and yeah, I'll just fill my mug and I'll come in 2 minutes. Okay. All right, guys. Sorry for the interruption. Let's get started. Uh, So now what we will do is we'll look into, yeah, so I hope you have understood the homework task. So your task is to evaluate the heat transfer coefficient on the right and left face. This is something that we need to do. But now what we'll do is we'll look into something which is heat generation inside a cylinder, inside a cylindrical system. Okay. And for that, I will stop here again for a couple of minutes. I want you to read the third problem that is in your screen. Okay. Okay, so I hope you have just browsed through the question. So let us try to understand what the question says. So it says that consider a long solid tube insulated at the outer surface R2, okay, and cooled at the inner surface R1 with an uniform heat generation Q dot within the solid. So there is this long solid tube, okay, which is basically insulated on its outer radius, and it is being cooled by a fluid at its inner radius, where now there is a heat generation that is being taking place inside the solid. Such kind of system in the physical world you see in nuclear reactors, okay. For example, these nuclear rods basically are cooled in this way. So in the nuclear rod, the nuclear reaction basically takes place, and that's why you can represent the heat that is being generated due to this nuclear reaction by a heat generation term, and then it needs to be cooled, okay, which basically is done by the cooling fluid, and these kind of systems are very common in nuclear reactors, okay. So it says, so this is the physical system. So now what it is saying is that obtain the general solution of the temperature distribution in the tube, okay. We need to obtain the solution of that. So basically we need to obtain the temperature profile. This is something that we need to do. In the second case, what they have asked us is, in a practical application, a limit would be placed on the maximum temperature that is permissible in the insulated surface. Okay, and specifying this limit as TS2, identify appropriate boundary condition that could be used to determine the arbitrary constants that appear in the general solution. This is something that we will see. Then they are saying is determine this constant and the corresponding form of the temperature distribution. So what they are saying is that, okay, in the first part, we will use the heat diffusion equation in cylindrical coordinate system to find what the temperature profile would be in this case. But if we integrate it, as you will see, we will see that we will get some constant. In fact, we will get two constant. That is typically because your heat diffusion equation is second order, so you'll get two constant in your problem. Now, in order to evaluate the constant, as we have seen it multiple times, we require boundary conditions. Okay, so what they're saying is that consider another boundary condition. See, one boundary condition is something that we have, which says that it is being cooled by a fluid. Okay, the second boundary condition, what they're saying is that they're specifying. Okay, so one boundary condition is not that. So one boundary condition. Sorry, I just said it wrongly. So the first boundary condition, it said is that it is insulated at the outer surface R2, which means your flux at R2 is basically equal to 0. In the second condition, what they have said is that in addition to this insulation at the outer radius R equal to R2, they have specified the temperature at that surface to be TS2. I will draw the schematic, and this you will be more clear on what they are saying. So they have said is that if now we have two boundary conditions, one at R2 we have your flux to be going to 0, and now in addition to this boundary condition at R equal to R2, they have specified the temperature TS2. Now based on these two conditions, since we will encounter two constants while solving the heat diffusion equation, we need to evaluate the constants using these two boundary conditions. Okay, this is precisely the second task that they have asked us to do. Okay, third task is that we know that there is heat generation taking place inside the slab, inside the cylinder, having radius R1 and R2. Okay, they're asking us that if this is the case, what is the magnitude of the heat removal rate per unit length of the tube? So try to understand what basically is happening. So inside the tube, okay, inside the tube there is basically a heat generation that is being taking place, and it is being cooled by a fluid which is flowing, inside basically the radius, which is flowing inside the radial distance r equal to 1. So I'll draw the schematic and it will be much more clear. So what they're saying is that if there is a fluid which is basically cooling this cylindrical rod, then they're asking that what is the heat removal rate that the fluid is taking away from the rod. Okay, that is the third question. The fourth question, what they're saying is that if the coolant is available at a temperature T infinity, obtain an expression for the convection coefficient that would have been to be maintained at the inner surface to allow the operation to be prescribed at TS2 and Q dot. So what they're saying in the fourth question is that if my fluid temperature now, which is basically cooling this cylindrical object, is at temperature T infinity, then what would be the heat transfer coefficient so that I maintain a uniform heat generation of Q dot and a uniform outer surface temperature TS2. Okay, so this is the four questions that basically needs to be answered in this problem. So what I will do is I will begin by drawing the schematic, and you guys need to help me on it. Okay, so what we will do is we have uh so let's first draw the rod here. So we have a radius, let's say R1. So this distance from the center, this distance, we will consider it as R1. Okay, maybe I write R1 there. And then we also have another, we so it's I hope you have appreciated the fact that this tube is a concentric tube, right? So it have an inner radius R1, and then let's say it have an outer radius R2. Let's say it have an outer radius R2. So this radius is basically R2. So now let's look at the information. They are saying that so if I draw the length, this tube would basically be something like this. And this will then extend to some length L. I'm not drawing the entire length, but yeah, this length of the tube is basically L. So try to understand that they are saying that this tube is basically insulated on its surface, which means this surface is insulated. Or maybe I will draw it something like this. So this surface is basically insulated. And by insulation, as we have seen in the first problem, it means that there won't be flux that will escape through this surface. Okay, there won't be flux that will escape through this outer surface. Okay, I hope this is clear. Of course, Q. This of course Q. Okay, so the no insulation. I mean, the insulation philosophy says that the Q dot, or I would say Q flux at R equal to R2 is basically equals to 0. Okay. Now, what they're also saying to us is that we have a cooling fluid. So this tube is basically cooled by a fluid, which means we have a fluid that is basically flowing through this space. Okay. This fluid is flowing through this space. All right. And maybe I would say you can pick any direction, maybe the direction of this flow. So first let's draw the axis. Let's say this is my z-axis. Okay, maybe this is my z-axis, which basically extends in this direction. Okay, and maybe your fluid is basically flowing through this direction, which means that this is the direction of the cooling fluid. Now, the cooling fluid, as I have said in the third problem, they have said that this is at temperature T infinity, and the heat transfer coefficient is H. This H is something that we need to figure it out. All right. And also, the final bit of information is that this rod, this cylindrical rod, basically this rod, this is generating heat at some magnitude Q dot, which is basically, so your Q dot is basically the heat generation. So this is your heat generation, I would say, in the rod material. Okay, having a unit of watt per meter cube. All right. So given this scenario, I hope the physical picture is clear to you. So given this scenario, okay, what you guys need to do is the first task is to obtain a solution for a temperature distribution. So we will do it now. So what you need to do is, yeah, and assumptions, of course, you need to write. So remember, now we are using the cylindrical coordinate system. So this direction, I would say this direction becomes my z-axis, and r-axis, you all know this, the direction that is in the radial direction. Of course, this is basically my r-axis. Of course, this problem is axisymmetric, so your theta direction doesn't really matter, but if you want to calculate, your theta direction would basically be in this direction. Okay, so I hope the coordinate system is clear to you. All right. By the way, this is your cooling fluid, as I have said. This is your cooling fluid. Okay, I hope the physical system is clear to you, but we basically did. I would stop here just for you to understand what we drawn on the screen. And then we will proceed with the solution of finding the temperature profile inside this rod, given that this is the physical scenario. Okay. All right. I hope the picture is clear to you. Maybe I'll wait for some more time such that you can understand what we did, and then we will proceed with the solution of this problem. All right, guys. So I think, sorry. Okay, so let's get started with the first task. Okay, so task one, as I have said, your task one is to find out the temperature distribution inside the rod. So it's basically evaluating the temperature distribution. Okay, so for this, what we need to do is you need to write the assumptions that we have seen how to do that. I will not repeat it again, but if you are solving this as your own, make it a habit of writing the assumptions. Okay, so we'll start off from the heat diffusion equation. From the heat diffusion equation. Okay, but now this is a cylindrical geometry, so we'll write the heat diffusion equation in cylindrical coordinate system. So I'll write it here in cylindrical space. So if you write that in cylindrical space, your heat diffusion equation basically comes out to be like this. So it is 1 by R ddr of R K dTdr plus Q dot, which is basically the heat diffusion term, and this is equals to 0. Okay, so this is your heat diffusion equation written in a cylindrical coordinate system, and I think you have in your like lecture classes you have seen ample number of times how this equation basically comes. So we'll not see how this equation is basically derived. The general idea is same. It comes from the heat, like the energy balance, but the nuances of how this equation comes, you can look your theory classes videos to basically have a idea if you have basically forgotten it. So we'll start it from here that this is the heat diffusion equation that we write in cylindrical coordinate. So what we need to do is remember the objective. We need to basically find this T as a function of R. Okay, this is T as a function of R. Remember, we are considering the heat dimension to be one directional. That is basically the common assumption that we take, which means that my heat transfer will be only taking place in the R direction. It will not be taking place in the Z direction and in the theta direction. Okay, I hope this is clear to you. That means that your temperature distribution is just a function of R, just like what we did in the slab system. Okay, so let's do this. So what I will do is I'll multiply this entire equation by R, which so this becomes ddr of RK dTdr equal to minus Q dot R, and that what I will do is I'll integrate it. I will integrate it with respect to R. Okay, so if I integrate it, it becomes basically like this ddr of RK dTdr. Now integrating with respect to R, and that's why this becomes minus Q dot R dr. So if you do this integration, this becomes RK dTdr. Okay, and this becomes what? This becomes minus Q dot by 2 R square plus C1. Okay, so what now? So what I will do is I will divide this equation once again by R, and that's why this becomes K times of dTdr, and this is equal to minus Q dot by 2R plus C1 by R. Now what? We'll again integrate it. So we'll again integrate it. Since we require the temperature, we'll again integrate it with respect to r. So if we do that, what we'll get? So it is just again integration of k dt dr, and this is dr, and this is minus q dot by 2r dr. We'll integrate it with respect to r. Then this becomes plus integration of c1 by r dr. Okay. So then what? Then this becomes k times t as a function of r. Okay. And then this becomes what? This becomes minus q dot by 4r square. This is the simple integration, and integration of 1 by r dr is just ln r, which basically this becomes c1 ln r plus c2. And then if I just divide this by k, okay, if I just divide this equation by k, this becomes t as a function of r, becomes minus q dot by 4 k r square plus, see here, c1 is a constant, c1 by k will also become a constant. That's why without the loss of generality, we can still write it as c1 because c1 is an arbitrary constant, right? And that's why we can just write it as c1 ln r plus. Similar analogy, c2 by k is a constant, which means without the loss of generality, c2 can be just written as an arbitrary constant c2. Okay, so this is your first problem, and this is precisely the temperature profile for this rod bearing so this is your temperature profile for the rod bearing a uniform heat generation Q dot, where K is the thermal conductivity of the rod, C1 and C2 are just arbitrary constants, as you have seen. Now what we'll do is we'll come into the second part of the problem, which involves calculating the constants C1 and C2, and for that they have given us two boundary conditions. See, the first boundary condition which they have said is that this surface is basically insulated, which means the flux at r equal to r2 is 0, which means if I use the Fourier's law, minus k dt dr at r equal to r2 is 0. This is one boundary condition that they have said. In addition to it, they have also said that the temperature on the surface is prescribed, and this is basically equal to Ts2. The temperature on this surface is basically to T at r equal to r2 is basically equal to Ts2. This is something that they have already said to us, and we will basically use these two boundary conditions in order to evaluate the two unknowns C1 and C2. Okay, so we'll do that. So the second task is to evaluate the unknowns So what are the unknowns C1 and C2? So we'll use the first condition. So the first boundary condition is basically the fact that, okay, your temperature T at R equal to R2 is equal to TS2. Okay. All right. So if we do this, what will you get? We will substitute this in maybe this equation 1. Maybe we'll write it as equation 1. Maybe we'll write it as equation 1a. So, all right, we'll also write the second boundary condition and then we'll do the substitution. So the second boundary condition, as you all said, is that the flux at R equal to R2 is 0, which means that your outer surface is insulated. And if I just use the Fourier's law, okay, if I just use the Fourier's law here, I'll just get minus k times of dt by dr at R equal to R2, and this becomes equals to 0, which means that your dt by dr at R equal to R2 is 0. And this is my second boundary condition. Okay, this is your first boundary condition and this is your second boundary condition. So now what you need to do is, it's very simple. You just need to substitute these boundary conditions 1a and boundary conditions 1b. I'll write it as 1b here. Maybe I'll just write it as 1b into this governing equations 1. Okay, so what you need is just substitute 1a and 1b into 1. Okay, so let's do the first substitution. The first substitution says that T at R equal to R2 is TS2, which means that I can just write it as TS2 equal to minus of Q dot by 4K times of R2 squared plus C1, okay, ln R2 plus C2. Okay, this is one condition. And if I use the second condition, that is, if I use the fact that my dTdr at R equal to 2 is 0, so for that, I just need to evaluate what is dTdr. Okay, so basically, if you evaluate this dTdr and basically, so 1 second, did I make any mistake here? Don't think so. Just hold on. I'm just thinking that did I make any mistake here? I don't think so. Yeah, okay. I think it's fine. Yeah. So anyways, if I just evaluate this dTdr, so your dTdr from equation 1 basically comes out to be what? So your dTdr, in fact, we calculated dTdr here, right? So dTdr is basically here only. So your dTdr is just minus q dot by 2kr. Okay, it's just minus q dot by 2kr. Okay, it's just this. It's just this. So this is your dTdr basically. This is just your dTdr. Okay, you don't need to again differentiate it because already we have integrated it and then integrated it from the heat diffusion equation and specifically like and implicitly calculated what dTdr would be. So this is just your dTdr, which is minus q dot by 2kr plus c1 by r, q by 2kr plus c1 by r, and at so what I have at r equal to r2, I have what I have. So at r equal to r2, hold on, did I do any mistake here? Okay, okay, I don't think so. Let's see. Okay, let's see. So at r equal to r2, your dTdr is basically equals to 0, which means that 0 equal to minus q dot by 2k times of r2 plus c1 by r2. And from here, you can evaluate what C1 is. So you can see that your C1 in magnitude comes out to be around Q dot by 2K R square. Okay, so this is your value of C1. All right, this is basically your value of C1. Now what we will do is we will substitute the value of C1, we'll substitute the value of C1 into the first condition, which is basically this. So if I substitute the value of C1 into this, I will basically get C2, which is the other unknown that we are trying to solve for. So we'll just substitute here. So therefore, TS2 becomes what? So TS2 becomes minus Q dot by 4K R2 square, R2 square, and your C1 is what? It is C1 times ln R2, so and your C1 is plus Q dot by 2K R2 ln R2, I think should be something like this. Okay, this should be R2 squared. Okay, this should be R2 squared. Your C1 is Q dot by 2K R2 squared, and that's why it become R2 squared ln R2. Okay, and then I have this C2. So from here, your C2, if you simplify, your C2 will come out to be eventually equal to TS2 plus Q dot by 4K R2 squared minus Q dot by 2K R2 squared ln R2. So that's it, guys. This means we have evaluated C1 and C2 from these two from these two boundary conditions. That is basically the fact that your surface is prescribed to a temperature Ts2 and the flux at R equal to R2 is basically equal to 0. And then we have evaluated this C1, which is basically equal to Q dot by 2K R2 square, and then your C2 is this term Ts2 plus whatever it is, whatever we calculated from here. Okay, so this is basically your C2, and now what we'll do is ultimately see what do we require. We require a temperature profile, right? So what we will do is we'll substitute the value of C1 and C2 into the main governing equation, which is basically into the main solution. Sorry, we'll substitute the value of C1 and C2 into the main solution, which is basically given by this equation 1, and then we will ultimately get the temperature profile subjected to the two boundary conditions that we used. Okay, so we will so the task is we will substitute C2 in equation 1, C2 and C1 of course, C2 and C1 in equation 1. And if you do that, you just do the math, you will get your temperature profile T as a function of R, okay, to be something like this. So it will be Ts2 plus Q dot by 4K R2 square minus R square, okay, minus Q dot by 2K R2 square ln R2 by R. So it's just simple. Just take this expression of C2, take the expression of C1, and just substitute it into the equation 1. And this is basically what you are supposed to get. Okay. So this is your temperature profile that we are trying to solve for. All right. So this ends the second part of the problem. I would wait here again for a couple of time, and then we'll just finish up with the remaining two problem, and we'll call it a day for today's session. In the meanwhile, if you have any doubts, you can just feel free to interrupt me, or you can just type it in the chat, or later on you can post it in the discussion forum as well of the course. Okay, so if you don't have any questions, let's look into the third part, what we need to do. So the third part says that they're asking us to determine the heat removal rate per unit length of the tube. And for that, what we need to do is, uh, so for that, what basically we need to do is I think the problem is clear, right? So basically there is this rod, okay, which was generating heat at some Q dot, okay, and then this rod will now basically dissipate the heat to the fluid. So your fluid is basically cooling the rod, which is basically taking heat from the rod to itself. Okay, so if that is the scenario, since we know that the outer surface is basically insulated, this means that whatever the heat that is being generated inside this rod will now go to the fluid. Okay, and in this context, they're asking us to evaluate. In this context, they're just asking us to evaluate what will be the rate of heat removal by the fluid from the rod. Okay, I think the picture is clear. So it's very simple now. We'll just use the Fourier's law. So the heat removal rate. So the third part is like estimating the heat removal rate. So for that, we will use the Fourier's law, and which says that your flux at any radial location is basically equal to minus K times your dt by dr, which means, so this is your flux. So if I want to calculate what will be the rate of heat removal, it becomes Q dot, or since we have already used Q dot in heat generation, we will just designate it as Q, which is basically your or what we'll do is we will calculate the rate of heat removal per unit length, which means it will just be Q dash, and this would be your flux multiplied by your surface area, and that's why this would become Q double dash times 2 pi R, and it's not 2 pi RL because we are calculating it per unit length. So remember, this is heat removal rate uh, per unit length. Okay. So this is your heat removal rate per unit length, and it is basically the flux multiplied by 2 pi R, and that's why this simplifies to Q dash. So your flux is minus K times dt dr into 2 pi R, so this becomes K times 2 pi R into dt dr. Okay, so this is your heat removal rate per unit length, and we already know the expression of T, right? So we know that your T basically is this. Okay, so all you need to do is you just need to evaluate this dt by dr from this expression of T. Okay, just need to evaluate. So if you evaluate this dt by dr, just all you need to do is just do a first derivative with respect to r in this equation. And then if you just do this, you will see that your q dot, which is the heat removal rate, is, so it just simplifies to something like this. It is just, so it just simplifies to, of course, we now need to evaluate this at r equal to r1, because typically, because this heat is being removed by the cooling fluid. So what you need to do is you need to evaluate this dt by dr and then substitute r to be equal to r1. And then if you just do this math, okay, I hope it is clear to you why are we like evaluating it at r equal to r1. See, the picture is clear, right? It's that the heat will be removed by this fluid from this interface of this cylinder, right? Which means whatever the heat that is being generated inside the cylinder will be dissipated to it by the flux. That is basically calculated from the Fourier's law. And if we calculate the flux at R equal to R1, it is exactly equal to the heat removal rate per unit length by the cooling fluid. Okay. And then if you do this, you will see that you can do it at your space, and you can see that Q dash eventually comes out to be minus pi times Q dot into R2 square minus R1 square. Or in terms of temperature, you can also write this in terms of temperature, but it's okay. Your Q dash basically comes out to be this. You can have a very nice inference from this expression of Q dot. See, this is again related to the control volume approach that we did. Okay, so it's like whatever the heat that is being generated by this Q dot has to be dissipated. Okay, so if you just do a heat balance between, or if you just do an energy balance, you will see that if you just write Q dot in minus Q dot out plus Q dot generated, and that is equal to 0, which means you will see that your Q dot out is basically the flux times the area, and this is equal to Q dot generated. And if you exactly do that, you will end up similarly getting this exactly the same equation that we got, which is basically pi times Q dot into R2 square minus R1 square. Just do the energy balance that we did in the last problem as well, and you will see that you will end up getting the flux as this. So you can, in two ways you can do it. You can either use the Fourier's law, or you can use the energy balance in solving this. Okay. The final task is to calculate the heat transfer coefficient, and we will end this problem by calculating the heat transfer coefficient here. So the final task is to calculate the heat transfer coefficient. So for this, what we will do is we will just use the energy balance at the interface, which says that your conduction flux basically is equal to the convection flux, or I would say not flux, but I would say that the rate of heat transfer per unit length by conduction is equal to the rate of heat transfer per unit length by convection. And we know that this Q dot conduction is basically equal to this, because this is basically your Q dot conduction. That's why this becomes minus 5 times what? This becomes 5 times Q dot into R2 square minus R1 square. And your Q convection, this is basically from the Newton's law of cooling, as we have seen that this is basically your H times 2 pi R, and here it will become R1 into the temperature at Ts1 minus T infinity. So this is just HA delta T that we have written. This is just HA delta T. Okay, that is typically because, once again, if I say that if I apply the energy balance on this interface, but I will see that the flux that is coming out from this rod to this interface is basically the conduction flux, which is Q conduction, and the flux that is going on to this fluid is Q convection. Okay, and a steady state, since we know that interfaces cannot store energy, okay, this means whatever the flux that comes inside the interface, it should be dissipated to the other end of the interface. Okay, and that's why at steady state we wrote that this conduction flux is equal to the convection flux. And if you do this math, okay, you will see that your H, the heat transfer coefficient, I think there will be some cancellation here. This pi and pi would just go away, and your H has a simplified value of Q dot into R2 square minus R1 square divided by 2 times of R1 into Ts1 minus T infinity, where this Ts1 is basically what the temp. So this Ts1 is not an unknown. Okay, just try to realize that this Ts1 can be obtained if we just put R equal to R1 in this temperature profile. Okay, It's not an unknown because we have already determined the temperature profile, right? Which means that TS1 is a known. The only unknown that we encountered is the heat transfer coefficient for what we are basically trying to solve for. And typically this is the value. So remember that this TS1, although it appears to be an unknown, it's not an unknown because the temperature profile inside the rod is completely known. This is basically T at R equal to R1 for the rod. Okay. All right, guys. So I think this is it. Then this ends the discussion on this problem. I think today we really solved some involving problems related to heat generation in slabs and cylinders. So I think you guys have appreciated how basically we need to go on with the approach and then try to correlate between the flux and the energy balance that we apply, and we see that irrespective of you calculating the flux through the Fourier's law, or you go on and calculating it from the energy balance taking and control volume approach, you will eventually encounter the same answer. Okay. And this is typically the idea, because obviously the Fourier's law and the heat division equation, these essentially are a big picture of the energy balance only. Okay. So this is the idea. I would stop here for some time. If you have any doubts, you can ask me, or else we will meet on Tuesday. Remember, the session, as I said it in the last, as I said it in the beginning, the live sessions, the NPTEL live sessions on which we are scheduled to have on every Saturday from 3 to 5. The session on 24th August, that is on Saturday from 3 to 5, is preponed to August 20, Tuesday from 6 to 8. And the session on August 31st from 3 to 5 is postponed to September 8th, Sunday from 3 to 5 p.m. Okay, kindly note that, as I said, you will receive emails from the NPTEL team to your to your course website. I will receive emails on that, but nevertheless, I will post it in the discussion forum of the group as well, such that we are on the same page regarding this. So what we will do is we will meet on this Tuesday, August 20, and we will discuss the problem that we will be solving for the next assignment, and so on and so forth. Okay. So with this, thank you very much for attending. And also remember that these readjustments of these dates are just for 2 sessions, and for all other sessions, we'll meet on uh, the usual Saturday timings from 3 to 5. Okay. As I will repeat, these readjustments in the date, that is the readjustment for the session uh, on August 24, which is preponed to August 20, and for the session on August 31, which is postponed to September 8, is just for these 2 sessions only. And for all other sessions, and we will meet every Saturdays from 3 to 5, as we do in our usual timing. Okay. So with this, like if you don't have any questions, we will stop here. We'll stop here and we'll end this class here today. Thank you all for attending, and like you can, so as you know, this is recorded and it will be posted in YouTube, so you can basically uh, like go through it. Like if you miss the session, you can basically go through it. The details of the session can be found in the website. The recording link will be shared in the website, and also these notes, as you know, is also being shared through a Google Drive in the course website. Okay. So thank you very much, guys, for joining today's session. So we end it here. We will see and we'll meet on Tuesday from 6 p.m. to 8 p.m. Tuesday meaning this August 20, Tuesday from 6 p.m. to 8 p.m., which is basically the special class that I was talking about. Okay. All right, guys. Thank you very much. I'll end the meeting here now.